Hi and welcome to Quick Add Math on equations and inequalities. We shall begin with solving multiple modulus linear equations as represented by the modulus of ax plus b being equal to the modulus of cx plus d. In the case of when modulus of a is equal to the modulus of b, a squared is also equal to b squared. Likewise, the modulus of ax plus b being equal to the modulus of cx plus d would imply that ax plus b all square being equal to cx plus d all square. With that being said, this technique can be used to solve for a modulus equation being equated to another modulus equation to solve for its x. Do also note that this would also apply for simultaneous equations where both y's are modulus equations. Now on to tutorial question 1, where we have to solve for an equation involving modulus parameters. This is different from the example that we've just been through. This is a quadratic equation with its main parameter as being the modulus of x plus 2. Therefore, we could start by equating y being equal to the modulus of x plus 2 and represent the equation in terms of y to solve for y. Having solved for y, it directly also means that the modulus of x plus 2 are the solutions of y, which would then allow us to solve for x. Next, we shall look at modulus linear equation within an inequality. Here is an example where we are to solve for a modulus 2x minus 1 being less than 5. You can view the above as if there are two equations, namely y equals the modulus of 2x minus 1 and y equals 5, and therefore be able to go on and plot their respective graph forms as shown on the right. For the given example, you have to solve for the modulus of 2x minus 1 being less than 5, and what you're interested to solve is the value of x where the line y equals the modulus of 2x minus 1 is below the line of y equals 5. This is shown as the bolded yellow line on the diagram. This is the domain at which x is between q and p, where p and q are the x values for the points at which the two graphs intersect. To cover, when we are asked to solve for the modulus of 2x minus 1 being larger than 5, this would result in x being less than q and x larger than p. Now, to get to the values of p and q, p can be solved from 2x minus 1 being equated to 5 and q with 2x minus 1 being equated to minus 5. In the case of the example, with p being 3 and q being minus 2, the required solution is when x is in between minus 2 and 3. Next, I wish to take an equation that we've done at the start of this video and subject this equation to become an equality represented by the modulus of 5x plus 1 being larger than the modulus of 1 minus 3x. As in the workings that we've done, this will get to the inequality having the product of 16x with x plus 1 being larger than 0, which will lead to the solution of x being less than minus 1 and x being larger than 0, as can be visualized on the diagram on the right hand side. Tutorial question 2. Solve the given inequality. The graph on the right shows the field for what we're looking for, which are the bolded yellow lines as shown on the right. As you should be looking at the outer band from the 2 points at which the two equations intersect. By algebraic method, you could equate 1 minus 2x as being less than minus 3 and 1 minus 2x as being larger than 3 to get to the solution. Tutorial question 3. Solve the given inequality having modulus functions on both sides. For such a question, you would square the equation, then rearrange the parameters to form a quadratic on the left-hand side with inequality against 0, factorize, and solve for x. Next, we shall look into cubic graphs representing cubic polynomials ax cubed plus bx squared plus cx plus d. It is important to know that its graph for a positive coefficient at its x cubed is shaped as shown, which is one that heads towards positive infinity for its y when its x heads towards positive infinity. In the reverse manner, its graph for a negative coefficient at x cubed is shaped as shown in red, which is one that heads towards negative infinity for its y when its x heads towards positive infinity. Here is an example of how we could go about sketching the graph for 3x cubed plus 8x squared plus 3x minus 2. We have in the past worked the maths for the cubic polynomial being equal to the product of x plus 2, x plus 1, and 3x minus 1. With all this, and knowing that the graph will take the shape as stated for a positive coefficient at its x cubed, the graph would therefore be one that will be intersecting the x-axis at the values of minus 2, minus 1, and a third. In the same manner, if we were to convert this cubic polynomial to being an equality that is less than 0, we could easily decipher from the graph that these are when x is less than minus 2 and when x is in between minus 1 and a third. Tutorial question 4. Sketch the graph for the given cubic polynomial. In this case, the graph has a negative coefficient at its x cubed and will intersect the x-axis at the values of minus 2, 1, and 1.5. With that, the sketch can be as below. Tutorial question 5. State the coordinates at which the graph of the given equation intersects the x-axis and sketch the graph. The x-axis is when y equals 0, so the required coordinates are minus 1, 0, and 2, 0. And with the graph having a positive coefficient at its x cubed, it implies the curve as shown. With there having two identical solutions, the turning point will also be sitting right on top of the coordinate representing the two identical solutions. With that, we could plot the graph as shown. Tutorial question 6. Using the equation from tutorial 5, solve the given inequality. For the given cubic polynomial to be less than 0, we could easily reference the graph to tell that the solution is when x is less than minus 1 and when x is in between minus 1 and 2. Tutorial question 7. Solve the given equation. It does look heavy until you decide to let y equals x to the power 4 and as such be able to rewrite the equation into one that is quadratic in nature, and this would solve for y as being 7 plus minus the root of 73 divided by 4. Knowing this, we could then equate the solution of y to being equal to x to the power of 4. Knowing that x to the power of 4 cannot be negative, the only solution for x to the power of 4 is when it is equal to 7 plus root 73 over 4. This equates to 3.886, which solves for x being equals to plus minus 1.40, correct to 2 decimal places. Tutorial question 8. Solve for the given equation. Again, it will not look as heavy once you equate y being equal to root x, and therefore creating a standard quadratic equation where we are to solve for y and making the solutions for y being equals to root x to solve for x. Tutorial question 9. Without having to spend the time to complete the full solution, I would just like us to just mention the substitution method to solve for the next 3 equations. In the first equation, you will let y being equal to x to the power of a third to form the quadratic equation, which we could then solve for y and then onward solve for x. For the second equation, you start by multiplying it with x to the power of 6. That could be rearranged to see a polynomial that is equated to 0. After, you'll let y being equated to x to the power of 3 to form a quadratic equation in terms of y, which allows us to solve for y and then onward solve for x. As for the third equation, all we need to do is to expand the first parameter of the equation and then allow y being equal to 3 to the power of x to get to the quadratic equation involving y. From here, you could solve for y and then onwards solve for x. We've come to the end for equation and inequalities. If you've liked what you've seen, do be on the lookout for our other tutorials.